going to look at the dry type transformer, the hermetic type transformer, and the conservator type transformer. We're going to look at the transformer components such as the core and windings, and then we're going to look at some of the other components that you're likely to see, such as the bushings, gas actuated relay, temperature thermometer, and the dehydrator breather. So let's get stuck right in, and we can start by looking at the heart of the transformer, which is the transformer core. So here we have a 3D model of a transformer core. We'll do a little spin. As you can see, this core has 3 limbs, and these 3 limbs indicate to us that this is a 3-phase transformer. The top and the bottom of the transformer core are known as the yoke, and these 3 pieces in the middle are known as the limbs. Each limb correlates to 1 phase of the transformer. The core itself is clamped together, usually using adhesive or some straps. If we look on the bottom here, we can actually see there are 3 straps. It's these items here. And you'll see there's also straps on the other side. 1, 2, 3. So the transformer core is clamped together, and the reason it's clamped together is because the core is not one solid block of metal. It's actually a series of metal sheets that have been clamped together. You'll actually call these laminate steel sheets. You can see on the side here that we've got these straight lines. These straight lines indicate to us that the sheets are of a different geometry, and as you've clamped them together you get this wavy pattern. If we can see, I'll move over to another limb. You can also see it over here, and that's because the core is not perfectly cylindrical. Now the reason that we clamp these very thin laminate sheets together is because we want to reduce the hysteresis and the eddy current losses. So we'll clamp all of the metal sheets together to form a limb, and then we'll clamp the metal sheet pieces together to form the yokes, that is to say the top and the bottom of the transformer core. Now each of the sheets is insulated from its neighbour, and the reason we do this is because we want to completely insulate or isolate each of these metal sheets in order that we reduce the eddy current and hysteresis losses. When we have electrical current flowing through the windings, and the windings wrap around each one of these limbs, then we create an electromagnetic field, and the core is going to become magnetized. The job of the core is to direct this magnetic field in order that we can get a high magnetic field density or magnetic flux. So that's what the core is doing. So we've got our limbs, 1, 2, 3. We've got the yokes at the top and the bottom of the core, and the core itself consists of very thin steel laminations that have been clamped together and have been isolated from each other, usually by using some form of lacquer or coating. And then once it's all together, we're going to clamp it together or perhaps glue it together, and that is our transformer core. The rest of the assembly that we're looking at now is simply to hold the core in position. So we can see in the section at the bottom here, that is to secure the core in the base of the transformer to make sure it doesn't move around. And we can see at the top as well, we also have this installation to secure it to the top of the tank. And again, this stops any movement of the core within the transformer casing. This type of core could be used for a dry type transformer, a hermetic type transformer, or a conservator type transformer. The design does not change that much. The only noticeable change that you will see is if you are using a single phase transformer instead of a 3-phase transformer like that currently shown. So now we've had a look at the transformer core, let's go and have a look at the next item on the list, which is going to be the windings. So now you can see we're looking at a dry type transformer. This is a type of transformer that is not insulated by a liquid, and the liquid may be oil or perhaps some sort of synthetic oil or even a biodegradable type of oil. But either way, this is a dry type transformer, also sometimes referred to as a cast resin type transformer. We can see it's got wheels on the bottom for moving it into position, and we've got these grey pieces. These are for cooling the transformer. If we go up, we can see the connections on the back of the transformer. But if we break it down into its components, we can see there are quite a lot of them. There's our core again, as we were looking at earlier. I'll see if I can actually assemble it slightly. We might see the actual shape of the core as it comes together. So you could see there are the straps that we were talking about earlier. These straps are used to clamp the core together. And we should be able to see the top of the core coming down at some point. Okay, the top of the core has now been installed. Unfortunately, we didn't get a good chance to have a look at it. And there are the low voltage connections coming out of the top. But let's explode it into its components again. So there's the core, and we can see here all of these circular items are going to be installed onto each of the limbs. Remember, one limb is one phase, so this is a 3-phase transformer. And within this group, we're going to have low voltage windings and high voltage windings. The low voltage windings are going to be installed closest to the core. So they're going to be wrapped around, or very close, should I say, to the core. Immediately after the low voltage windings, we're going to have high voltage windings. So we've got our primary and secondary windings installed, and if we push the play button, we can actually see them coming down onto the core. Here come our clamps, there comes some sort of insulator most likely, and here comes some windings and the HV windings that go on the outside. Once that's all assembled, it's going to look a lot like this, and we can see by looking at the back what type of wiring configuration that transformer has. The windings themselves are going to be made of copper or aluminium. Aluminium is usually used if there is no consideration to space. If you have a lot of room, you can use an aluminium type transformer. Generally, they'll be bigger than transformers that use copper for the windings. This is because the conductivity of copper is higher than aluminium, and their ability to carry current is also higher. However, aluminium is cheaper, and if you've got the space, then you can install a transformer with aluminium windings. But just remember, low voltage windings, they're going to be wrapped first around the core. High voltage windings are going to be wrapped second around the low voltage windings themselves. And then we're going to assemble the whole thing together. The windings themselves are going to be either copper or aluminium. And that is our transformer as we have it now. The core and the windings are the most essential pieces of the transformer. Technically, you can even manufacture a transformer without the core, although it will not be very efficient. The dry type transformer that we're looking at now is the simplest of the three that we're going to look at. And this dry type transformer consists of only the core, windings, and some cooling fans on the bottom. Let's now have a look at a hermetic type transformer. So here we are, we're now looking at a hermetic liquid immersed transformer. Let's have a spin. We can see on the top that we've got some low voltage bushings. That's these 4 thick ones here. The reason they are the low voltage bushings, or the reason that you can tell, is because the connections are very large. The reason they're large is because the voltage is low and the current is high. So that's a giveaway that the low voltage bushings are these 4 here. If we go on the other side, we can see the high voltage bushings, and that would be these 3 here. 1, 2, 3. The giveaway for those is simply that the voltage has been increased, therefore the current has been reduced. So we can see the current carrying pieces of the bushing. That's this metal piece here, and this one over here. Those pieces are going to be a lot thinner because the current they carry is going to be a lot less. However, the voltage is going to be higher, and that is why they have more insulation than the low voltage bushings. So if you step up the voltage, you're going to need more insulation, and if you step up the current, then you're going to need a thicker conductor. Let's break this down into its individual components again, just to have a look, see what is inside the box. And we can see there is our transformer core again, 3 limbs, that's 3 phase. We've got the 2 yokes, one at the bottom, one at the top. Then we have our bushings, and all of that can be assembled again to complete the hermetic type transformer. So essentially, the hermetic type transformer is a dry type transformer, but with a box around it, or a casing, that is full with a insulating liquid. Now this insulating liquid is typically mineral oil. About 95% of the time it's going to be mineral oil. And the whole thing sits in a bath of mineral oil. The reason it's called hermetic is because it is totally isolated from the atmosphere, or from the external environment. If you think about it another way, just imagine it's a hermit. All of the parts within the transformer don't want to come into contact with anything else, a bit like a hermit who lives in a cave on a hill. So this transformer is classed as hermetic because the internal parts don't want to come into contact with the outside. Once the transformer is sealed and the casing is sealed, it shouldn't be reopened again. However, there are exceptions to this, such as when you perform oil analysis, etc., but this depends upon the manufacturer. We've already discussed the bushings. Let's have a look at a few other items that we can see. We've got a filling pipe, that would be this area here. We've got some lifting bolts, or some lifting eyes, that's 1, 2, and another 2 on the other side. So that's for positioning the transformer or for installing it. There's the other 2, 1, 2. And then we've got a temperature indicator. Zoom in, we can see it here. And that's going to measure the temperature of the insulating liquid, which again might be mineral oil, or perhaps it will be silicone, or perhaps it will be some sort of synthetic ester, which is more or less a biodegradable oil manufactured from plants. If we zoom out, we can see that the casing itself is not perfectly square. It's got these fins attached to the side. These fins are used for cooling the transformer. What's actually going to happen is that some of the insulating liquid is going to absorb the heat generated by the transformer, and it's going to pass that heat on to the fins, and the fins are going to pass the heat on to the air. So the reason for the fins is to increase the contact surface area between the tank and the air, and this means we're going to get a much higher heat transfer rate. If we can keep the transformer cool, then we can also load it more heavily, at least up to a point. important to realise that if you can keep the transformer cool, then you'll also extend its useful working life. Overheating is typically one of the big killers of transformers. Let's now have a look at the conservator type transformer, which I think is the most interesting and has a lot more components compared to the dry and hermetic type transformers. So here we are, we're now looking at a conservator liquid immersed transformer. The reason it's called a conservator type transformer is because of the tank on the back, which is known as the conservator tank. That is this item here. We can see the bushings passing through the transformer casing and pointing upwards. As you can see on the left side, there are 4 high voltage bushings and 3 low voltage bushings. The high voltage bushings have more insulation and the low voltage bushings have less insulation. The purpose of the bushings is simply to connect the internal windings of the transformer to the outside electrical circuit. And we want to do this without raising the electrical potential of the tank itself. And that's what the bushings allow us to do. They allow us to pass the cable through or to connect the electrical circuit from the inside to the outside without raising the electrical potential of the transformer tank itself. Let's go over to our conservator tank again. The conservator tank is installed to allow for expansion of the insulating liquid when it gets heated up or when it cools down. The transformer is heavily loaded, then the insulating liquid is going to heat up and it's going to expand upwards. When the transformer cools down, the insulating liquid is also going to cool down, and then the insulating liquid level is also going to drop. So as we heat up the insulating liquid, it's going to expand, and as we cool it down, it's going to contract. In order to know what the level is, we install a MOG, and this is a magnetic oil gauge. We can see here the temperature. At 20 degrees we should have this level. So if we have 20 degrees now, the level will be here. As the temperature increases, the level will increase. This is not a temperature gauge, this is a level gauge. The 20 degrees Celsius is just for reference what the level should be at that temperature. If we look also on the bottom, we can see these 2 red lines or 2 red triangles. These are used as low level and low level alarm set points. It's important that we maintain a good head of insulating liquid within the conservator tank, because if that level drops down, we could get a catastrophic failure of the transformer, and obviously this is not what we want. If we look inside, I can show you the working lever. So there is the lever or the float, and you can see that as the level would increase, the float would be pushed upwards, and as the level decreases, the float would sink back down again. So that's how it works. Just remember though that this lever and float is not connected directly to the outside gauge. It's actually connected magnetically. It's coupled magnetically. That's why it's called a magnetic oil gauge. So we have a form of level measurement here on the side of the conservator, but there is also an interesting component fitted below the conservator, and this is known as a dehydrating breather, sometimes called a silica breather because it uses silica gel. As the transformer heats up, the liquid is going to expand, or the insulating liquid is going to expand, and we're going to push air out of the conservator tank, and it's going to come out through the silica breather. Let's just go up and see if I can find the holes where it comes out. Okay, so we can see the holes in the side of the breather, and the air is going to be pushed out through these holes because the liquid is expanding in the conservator tank, and it's going to be pushed through the silica gel breather and then out of these holes to atmosphere. When the liquid cools down, because the transformer is perhaps not so heavily loaded, we're going to draw air back in through these holes again, and then it's going to be drawn into our conservator tank. And that is the problem. If we're drawing air directly into the conservator tank, we want to ensure that it does not contain any moisture. If it does, we're going to get a problem. This may lead to a buildup of sludge when the moisture comes into contact with oxygen. Not only that, but the dielectric strength of our insulating liquid is going to be reduced. So these are all negative effects. So what we'll do, we will pass the air through a silica gel breather. That is this item here. It's full of silica gel beads. And the silica gel beads will remove the moisture from the air. As they remove the moisture, they're going to change colour. And when the colour has changed by 3/4, we know it's time to change the silica gel beads. So the colour change is purely for a visual indicator to see how saturated the silica gel beads are. Once the air has been dried, it's going to pass into our conservator tank. There is one other interesting aspect of the silica gel breather, or the dehydrating breather, and that is the oil cup on the bottom. And this is used to separate dust particles as the air is drawn in and through the breather. So we use this oil, or the oil cup, to attract bits of dust, and as the air bubbles through the oil, we're going to separate the dust particles or foreign bodies from the airstream, and that's going to ensure that we don't get any dirt or dust going into our conservator tank and mixing with the insulating liquid. So the dehydrated breather consists of an oil cup for separating dust particles and other foreign bodies, and a silica gel breather, or a dehydrating element, which is then used to remove moisture. The reason I call it a dehydrator sometimes instead of a silica gel breather is simply because the dehydrating medium may not be silica gel. It might be something different. So don't always assume that it's going to be silica gel. It's just that silica gel is used 90% of the time. Let's now have a look at one of the most important pieces of the transformer, and this is the gas actuated relay. The gas actuated relay is contained within this square box. You may also have heard the term Buchholz relay, although the Buchholz relay and the gas actuated relay are slightly different. A gas actuated relay protects against small electrical faults within the transformer and large electrical faults within the transformer. A Buchholz relay protects against small and large electrical faults, but also against a low insulating liquid scenario. So, if we have a small electrical fault within the transformer, we're going to heat up the insulating liquid, and this is then going to generate small bubbles of gas. The small bubbles of gas are going to slowly accumulate within the Buchholz relay. They're going to push a float downwards, and then we are going to set off an alarm which tells the engineers that there is a small electrical fault within the transformer. If we have a large electrical fault, we're going to get a sudden increase in pressure and a large pocket of gas. This pocket of gas is going to rotate a paddle, and that is going to shut down our transformer. Those are the two functions of a gas actuated relay: to alarm when we have slowly accumulating pockets of gas that are caused by small electrical faults, and to shut down when we have sudden large increases in pressure and gas that are created by large electrical faults. The Buchholz relay itself has a third and final feature, and that is to shut down the transformer in the event the insulating liquid level becomes low. We can see that it's installed between the conservator tank and the main tank. If the level was to come down to here, we would trip the transformer, and that protects the transformer then and ensures that we do not get a catastrophic failure. If we zoom out, you can see that we have different cooling fins on the side of the transformer this time. The reason that these cooling fins are larger is because we need to get rid of more heat. I'll just rotate around the side. You can see that we've got an entire radiator this time. The liquid enters the top of the radiator, it cools down, and then it passes out the bottom. And we'll have natural convection in order that the process continues, and we can cool down the insulating liquid as much as possible. If we go to the end, we can actually see that we've got some fans, and these fans will start once the temperature of the insulating liquid becomes quite high. You can see now that they're running. That means the transformer is heavily loaded, and we need to pass air over the heat exchanger or the radiator in order to get a greater cooling effect. If the fans are running like this, or if we have fans installed, we will say that the type of cooling employed is forced air. The second type of cooling that is described would be the cooling associated with the insulating liquid itself. In our case, we have a natural convection process. So this transformer is an oil natural air forced type transformer, or ONAF as it will be written on the nameplate. Let's go over to the end of the transformer, and we can see we've got a control box. This control box or control cabinet is used to house some of the associated machinery with the load tap changer. The load tap changer is mounted in this section here, and this type of tap changer is mounted directly within the transformer tank. That's not always the case. Sometimes the transformer will be mounted externally, or perhaps it will have its own compartment within the transformer tank. The disadvantage to having a tap changer directly within the tank is simply that it shares the same insulating liquid as the transformer. That means that when you sample the insulating liquid and start to look for faults or telltale signs, such as large amounts of acetylene or ethane, you're not going to get much reliable information from your sample. If the tap changer is mounted in a separate compartment or externally to the main tank, then you can sample the main tank. You can then send the sample away for analysis. You can look at the gases that are present within the insulating liquid, and that will give you a good indication as to what faults, if any, are present within the transformer. If we go this way, we can actually have a look now at the final piece of the transformer, or the final component, and that is a temperature indicator and temperature thermometer. The thermometer has been mounted within the tank, we can see it here, and the indicator is mounted on the side in order that engineers, as they walk past, can look at the temperature gauge and assess what it is and if we're operating within normal conditions. The red needle itself is used as an alarm set point. If the black needle should come around and surpass the red needle, we're going to get an alarm. The other red needles that we're looking at now are mostly used for cut-ins and cut-outs for fans and cooling pumps. So that was a very brief introduction to transform